Hi, welcome to this particular module, and in this module we will see nanostructures of sensing layers, particularly metal oxide nanostructures and electronic module that can be attached to a sensor. In last module what we have seen? We have seen the use of bulk micromachining and bulk plus surface micromachining to form sensors that can be used to detect volatile organic compounds, right. So, if you see the slide, what you see, this is bulk micromachining, this is bulk plus surface micromachining, this is a prototype that is packaged individual sensor chip, and we can see that using 100 micron diaphragm and using 2 micron diaphragm, suspended diaphragm, there is a huge difference in terms of temperature for the same amount of power. Now, to form nanostructure of zinc oxide, you can deposit zinc metal, thin film of zinc metal, and heat it in a presence of oxygen at different temperature for certain amount of time, right. So, what we found is that if you deposit zinc metal and if you heat the metal at 500 degree centigrade for 2 hours, you get nanostructure of zinc film as shown here. But if you increase the time from 2 to 4 hours, this is what you get, and further increasing time to 6 hours, you get nanoflakes along with a combination of nanowires, and this particular structure is better because instead of using thin film we are using nanostructures, and using nanostructure will increase the surface to volume ratio. So, when surface to volume ratio is high, the sensitivity of a sensor would be high. So, thus using a nanostructure of a metal oxide material or metal oxide nanostructure, we can improve the sensitivity of our sensor rather than using the thin film of zinc oxide or a metal oxide material. So, if you see the screen, what you see here is a beautiful zinc oxide nanoflakes and nanowires. It is a combination of both, and this is at 10 kx. All 3 images are at 10 kx. These are all SEM images, scanning electron microscope. We will see the characterization techniques, in that we will understand what are the kind of microscopes, and as I said, the zinc film should be extremely thin. In this case we are using 0.5 microns, or you can say 500 nanometers. So, 500 nanometer of a zinc thin film is used, and then it is annealed in the presence of oxygen at 500 degree centigrade for 2 hours, 4 hours and 6 hours. So, this zinc film will sit on the sensor, this zinc film will sit here, right. So, this is zinc oxide nanostructured as a sensing layer on interdigital electrodes, and everything is on 100 micron diaphragm, right, 100 micron diaphragm. Okay. So, you can use a copper oxide nanowires, you can use a WO3, you can use SNO2, you can use IN2O3. You have variety of options to use and to see which one would be sensitive as well as selective for a particular VOC, right. You see, sensitivity we can improve. What about selectivity? Selectivity is a important aspect, right, because from a group of VOCs that we have to selectively detect one particular VOC. So, how can we detect particularly one VOC? So, there can be selectivity for this kind of individual sensor for different VOCs is not so cool. So, what we are doing, we are using temperature, and at different temperature this sensor will show a sensitivity to particular VOC in higher amount, better sensitivity to particular VOC than the other VOCs. But single sensor cannot be selective and sensitive both. So, to improve selectivity we can use a group of sensors, and that group of sensors can work as sensor array, and that array if we connect with artificial intelligence or ANN, artificial neural network, then when we generate lot of data depending the amount of VOCs or the combination of VOCs that we are experimenting with, and we train our network, we train our neural network, then a complete system can selectively tell what is the particular VOC of our interest in the group of the given VOCs and what is the concentration, right. There is a whole set of experiments, and that is what people call as electronic nose. When you talk about nose has lot of sensors, right, and these sensors are connected through olfactory lobe to your brain, and artificial neural network, in our case it is a neural network, right. In the nose, which is electronic nose, you have to use ANN. So, coming back to here, what we understand is that we can use this sensor and we can design several kind of sensors depending on using micromachining, right, using micromachining. So, now if you see the nanostructures are here, and how we can know the concentration of VOC, right. So, we need to take a chamber. So, let me first show you the chamber. I will just go to that particular slide and then we come back. So, if you see, this is the chamber inside and sensor is placed inside the chamber. So, we are understanding how to evaluate the performance of one single sensor. Okay. So, just understand this particular thing. Okay. So, we have a chamber and we have a bubbler here, okay, and the gas is passed through this bubbler and this gas will be inserted inside the chamber. So, what is the concentration of, so if you see here we have a bubbler, right, and in which we have our VOC of interest. So, we have acetone, and this acetone, the vapor of acetone is carried into the chamber, right, along with nitrogen. So, we will see how the concentration of this acetone can be determined in this particular chamber. That is what we are interested in. What is the concentration? Is it 10 ppm? Right? Is it 20 ppm? How you know? How you know what is the concentration of the acetone in this particular chamber? That is what we are interested in to understand, and that is why to understand that we need to understand this particular formula, which is right over here. So, the VOCs were introduced. So, how can we get this data? How we were able to get this data, right? So, to get this data, the VOC vapors were introduced in the chamber by bubbling nitrogen through the VOC maintained at room temperature, right. The VOC that was that we have seen through bubbler was maintained at room temperature, right, and the N2 was passed through this VOC. Right, nitrogen was passed through this VOC. The desired concentration of vapors was obtained in the chamber by controlling the flow rate of N2 through particular VOC and adding pure air through a separate gas line, right. We need to change the concentration. So, what we had done, we are introducing the vapors by controlling the flow of nitrogen through a particular VOC. So, assume that this is a VOC and we are introducing nitrogen and we are introducing this in a chamber. Along with that, we are also introducing pure air, right, pure air. This is our VOC. The concentration of vapors was calculated using the following equation, right, which is C equals to P star into L divided by 760 minus L whole division by P star into L by 760 minus L plus L star into 10 to the power 6, 10 to the power 6. Now, you see here. In this case, L and L star are gas flow rates of N2 through bubbler. L and L star are the flow rate of gas of nitrogen through bubbler and air respectively, while P star is a vapor pressure of VOC measured in millimeter of Hg at room temperature, right. So, if we know, we already know, right, what will be the vapor pressure of particular VOC. For acetone it will be different, for ethanol it will be different, for every VOC the vapor pressure will be different at room temperature. So, we know this, right. Now, we also can know what is L and L star are the gas flow rates of N2 and air respectively. So, L is a gas flow rate of N2 and L star is a gas flow rate of air. So, using this equation we will know what is the concentration of VOC that we are measuring, right. Now, you see here the response of the sensor at different temperature we are measuring. Now, at 50 degree centigrade, you can see that the response to methanol, right, is higher compared to acetone, ethanol and IPA, while in case of 75 degree centigrade the response to acetone, sensor shows more sensitivity to acetone, and at 100 degree centigrade the sensor is showing a higher sensitivity for ethanol, right. Change in resistance, since ethanol, methanol, acetone are all and IPA are all reducing gases, the resistance of the sensor will decrease. If it is an oxidizing gas, the resistance of sensor would increase for zinc oxide as a sensing layer. So, you can clearly see that the resistance is decreasing for when you introduce acetone, methanol, ethanol and IPA, but the change in the resistance is higher for different VOC at different temperature. That means, the sensitivity is also depending for a particular VOC is dependent on the operating temperature of the sensor. Then in this particular all three cases the concentration of VOC is 200 parts per million, 200 parts per million. Okay. Now, comes our case where we were talking about a sensor on a diaphragm, sorry, right, or a sensor on the suspended diaphragm, right. You understand all the blocks are here, right. Now, in both cases what happens? In both cases we have seen that the temperature, so temperature here for 120 milliwatt of power was 120 degree centigrade. In this case surface plus bulk micromachining temperature was 300 degree centigrade for 120 milliwatt of power, right. This is the advantage that you keep on reducing if you have these suspended diaphragm which is about 1 micron or 2 micron in thickness, right, and you have this diaphragm where it is 100 micron in thickness, then compared to fabricating a sensor directly on silicon without creating a diaphragm, right. This is better because now we can reduce the power and achieve a temperature, but this is even better surface plus bulk because at the same power we can even have a better temperature. But in both the cases A and cases B compared to case X, the mechanical strength is reduced. Compared to X, A and B, the mechanical strength of the sensor is low, right. So, what can be an alternative technique such that we can achieve a higher temperature at lower power and have mechanical stability like X. We can have a higher temperature at lower power and still have a mechanical stability as good as the starting silicon substrate. So, if you see, this is a schematic of that sensor, right, and it is a blown up diagram fabricated on a planar thermally isolated MEMS platform, planar thermally isolated MEMS platform, you can see here. So, you have silicon and then you have thermally grown silicon dioxide, and then you have silicon dioxide sputter deposited, followed by an insulator and a nickel microheater, insulator, interdigital electrodes and nanostructure zinc oxide, right. So, let us see what we are doing here. Now, I will not draw individual steps in this particular case, since we know how photolithography is done, right. So, the first step is step number A, you take a silicon substrate. Step number B, you grow a oxide. So, oxidized silicon, you can see SiO2 on both sides. Step number C is you create a pit. Now, you know how to create a pit, we just took an example in the last module, right. You can create a pit by bulk micromachining. Then D, you fill this pit with silicon dioxide. Last example, we have filled the pit with sacrificial layer of zinc oxide. Here silicon dioxide is not sacrificial layer. Okay. So, you have to fill the pit with silicon dioxide, you can do sputter deposition and then you planarize this pit. So, you can see here, you can, this is also oxide, this is also oxide, this is SiO2, but it is thick, about 5 microns thick, alright. So, you create a pit, then fill the pit with silicon dioxide and planarize it. Once you planarize the pit, on that pit you can now perform the same steps like depositing nickel and patterning nickel microheater, depositing silicon dioxide and opening the contact, right. You can see here, if I go here E, F, G. E is patterning nickel microheater, F is depositing silicon dioxide on microheater, G is opening the contact, right, by etching silicon dioxide from the contact area of the microheater. H is to deposit aluminum as a metal for interdigitated electrodes and pattern it, and I would be to deposit nanostructure zinc oxide or to pattern nanostructure zinc oxide using lift off technique, right, using lift off technique. So, what is the advantage? What is the advantage of doing it? Now, you have silicon dioxide filled here. Silicon dioxide is thermal insulator, it is an insulator to heat as well, right, that is why it is thermal insulator and of course, it is an electrical insulator. So, the loss, the heat loss from the back side of the wafer is reduced because now we have thermally grown, we have thermal insulator filled in the pit on which the entire structure is fabricated, which is our sensor, right. So, small change, because of this what we get is an interesting data, right. Sensor using the technology that is right over here, creating the sensor on a filled pit with silicon dioxide, which is a thermal insulator, right, compared to sensor on oxidized silicon substrate. So, what we are doing is we have sensor on oxidized silicon substrate and we have sensor on a pit filled with silicon dioxide, and you assume that there is a sensor block here, What we found is that the mechanical stability, you see mechanical stability is still same, right, is still same, mechanical stability is still same, but the structure, the sensor, here what we have done, we have 5 micron pit filled with SiO2. By doing so, we are creating a thermal insulator, and that is why the heat loss from the back side of the wafer will be reduced, and thus the difference in the temperature that we get for the same amount of power is tremendous. You can see here, if I say about 200 watts, 200 milliwatt, we are achieving 450 degree centigrade, while for this particular substrate we are around 150 degree centigrade. You see a difference of 300 degree centigrade, 300 degree centigrade, right. If this is my 450 and this one is 150, I have a difference of 300 degree centigrade at the same power when I compare with the silicon substrate and sensor fabricated on silicon substrate, and my mechanical strength is almost similar, right. So, what changes we have done? Just a small change of creating a pit and filling with silicon dioxide, right. So, a small change in the structure can get you what you desire, right, and this is how we have created our sensor, right, and we call this sensor as sensor that is fabricated on a planar thermally isolated MEMS platform, planar thermally isolated MEMS platform. Okay. Now, once you have this, you have to connect your sensor to the electronic module, is not it? We have to connect our sensor to the electronic module. How can you connect sensor to electronic module? So, what should be the block diagram? The block diagram of sensor module incorporating sensor chip, signal conditioning circuit, and the display device is shown here. So, you can see here there is a sensor, there is a bias generator for bias compensation, there is a buffer, and to this after bias compensation we connect it to the instrument amplifier with variable gain, which is further connected to a microcontroller and finally a display. So, if you see this particular case, it is nothing but a Wheatstone bridge, right, and here you have a sensor with heater, you have a sensor with heater, right. So, you have a buffer here, buffer 1, buffer 2, the difference, this is a differential amplifier, and you can see here what will happen. Let us say initially the sensor, the resistance are at same value. So, let us say this will be having 2.5 volts, this will also have 2.5 volts. So, the output should be close to 0, right, if because there should be nothing if you balance your bridge properly. Now, when you change your, when the sensor senses a VOC, when a sensor senses a VOC, resistance would decrease. This reduce in resistance will cause a change in the potential divider here, and the voltage that you obtain at this end would be different than this particular end, right. So, the difference in the voltage, would be so initially of course, you have here 2.5 volts, right, 2.5 volts, you have here 2.5 volts. So, the difference should be 0, right, difference should be 0, but when the sensor senses a particular VOC, this 2.5 volts will change, and whatever the new value is, the difference of that value would be amplified by this differential amplifier. Along with the advantage here is that the noise will be also differentiated, the noise will there will be difference of noise as well. So, we are taking care of the noise as well, and of course, if you use instrument amplifier, that is a beauty that we can reduce the noise signal. Then it is further connected to a buffer, which is connected to pin 2 of your PIC of microcontroller. It is 16F877A, and this controller is connected to your display, just a small simple LCD display GHD162A, and corresponding to the change in the sensor value, that is change in resistance. This change in resistance we can show in terms of parts per million and in terms of vapor concentration, right. So, it is a tremendously easy electronic module to understand, right, with a sensor head and electronic conditioning circuit. Again, if you have any confusion, do ask, any confusion in this, do ask, okay. Any confusion in the earlier lectures also, please feel free to ask. Okay. So, how can we design this? We can design a quad op amp, we can take a quad op amp LM358 and then we can use all 4 op amps in this one, you can see here, right. Okay. Now, if you see here, right, like I discussed, this is a chamber, is a electronic module, right, that is connected to your display, and then we can measure the concentration of VOC, right. We can measure the concentration of VOC. You can see here, right, you can see here, it's a, we can control the gases, right. There is a needle valve to control the gas, and we can have a better control if we have a mass flow controller. Mass flow controller can be used to better control the gases. We have here VOC, right, of our interest, and then we are inserting it, and the gases are the gases of VOCs will come out, right, after the reaction. The sensor has indicated heater. So, once the sensor saturates, let us say for a given VOC, we heat it for certain times to get back to its base value, right. Baseline resistance is obtained again once the readings are once the measurement is done, right. Now, let us take an example of another device, and that is a 2-dimensional scanner driven by angular vertical comb actuators, right. It is a angular vertical comb actuator, you can see here, and here we are using a process called deep reactive ion etching, right. So, this is a mirror, and this mirror can be tilted with the help of this angular actuators, right. So, there can be different techniques. One technique can be, you can have a thermally actuator that can work on the thermal property. That means that if you change the thermal property, the temperature of that actuator, it will start actuating, which will cause the bend in the micromirror, right. So, one application, and of course, when you have to create this, as you can see here, front side etching, and then you are using back side etching, and clearly we can see that not only surface micromachining, but a bulk micromachining is used, right, to finally etch out our comb actuators, right. The more about this, you can find it in a Micromachine, the 2D scanner driven by ABC actuators, in a paper by P1 ETL. Okay. So, the point here that I want to make is that you can use micromachining, that is bulk plus surface micromachining, to create several structures of our several structures of various devices. Okay. So, let us see now what exactly is a dry etching. Okay. What is a dry etching? So, you have to load your wafer inside a chamber, there is a gas in and there is a gas out. Like I said yesterday, DRI, it uses C4H8, SF6 as well as helium and argon. So, and of course, CF4. So, here you see that there is RF power and is a reactive ion etcher. When you put the wafer, it will be etched in a direction. So, most of the absorbed species left absorption site without doing anything. So, you have the isotropy, where in case of the plasma etching, you will have anisotropy, which is S equals to 1, and the wall that you get is vertical compared to wet etching. This is how you get. So, I will show you an example that where you can use a DRI. We have just seen a micro actuator, we will see one more example where you can appreciate how does the DRI etches the silicon. So, DRI can be physical or chemical process or both. Ion beam etch, a physical process, gaseous chemical etch, plasma etch, reactive ion etching and deep reactive ion etching. So, dry etching can be not DRI, dry etching can be both chemical based and physical based, and we are interested in understanding DRI in particular or RI. So here you can see reaction here. Reaction is what momentum transfer by physical bombardment takes place at every shot, usually sputter of a few atoms, and so S is approximately equal to 1. So it is etched physically, and then gases are used to smooth the surface, smooth the boundary. Okay. So what we can see? We can see this is a process which is used by Bosch, and that is why it is called Bosch process to etch the silicon. So you keep on etching the surface, and then you keep on smoothing the wall, keep on etching the surface and smoothing the wall. So this is a video which will tell you how a DRI system can be used for etching a silicon wafer. Let us see the video, and then we will continue our discussion.
Welcome to the STS room. We are going to explain you a quick overview of how to operate the STS machine. So the first thing to do is once you arrive here into the room is to check the tag to see if the CDO is off, or otherwise if the machine has any problem and cannot be operated. In case that the tag is down or like hidden, you can operate the machine normally. The first thing to do is like come next to the screen of the room, to the small laptop, and log in. Once you are logged in, you have to proceed to the gas chase next to the STS room. The first thing to check in the gas room, the gas chase, is like the CDO box. The CDO box is responsible of neutralizing the exhaust gases from the STS. So by burning them, it makes them harmless. The thing that we have to check is that all the lights are green, and the temperature it's within parameters, as well as the levels of the water, nitrogen and oxygen. Once we check that everything is under working conditions, we will check if the operating gases are flowing. As you can see, the gases are in this side of the room. We're going to be using the first 4 gases that are the C4F8. So we have to check if it's in use. Then the SF6, the oxygen and the helium. If once you arrive here you notice that any of the tags says that they are not in use, please contact a super user or staff to turn them on. Once you are inside the room, take advantage to check for any weird noises or like funny smells. If everything is in place, you can proceed with operating the machine. Back in the STS room, the first thing that we will do is check the STS tower, and then we will record the conductivity of the water and the temperatures on the STS, the HCU 5 and like 3 and 1. So we will record the values, and once we have recorded the values from the tower, we will go to the computer to record the other different values that we have to record. The ones that we need are going to be the high vacuum pressure, the Kapman pressure, the 4-line pressure, and the load lock pressure. If you have any problem finding any of the values in the screens, you only have to go on top of them to see what are their values. Once we recorded the parameters, the first thing that we have to do is change the operator mode on the software of the STS. In order to do that, we go to Edit, Operator Mode, and we change from Monitor to Development. We press Change, and then we log in the password. We press Return twice, and we change now to Development Mode, where we can operate the machine. Now the first thing to do is to load the desired wafer to the load lock chamber. We do that going to the transfer window and pressing Vent. Once we press Vent, we have to wait for the load lock chamber to reach atmospheric pressure. Once the transfer chamber is under atmospheric pressure, we open it, and we will charge the desired wafer into the chamber. As you will see, like usually the wafers have a flat, and loading carousels we have a small line. Please align the flat with the line on the desired spot. Once we have the wafer properly loaded, we close the load lock chamber and we go to the transfer window and we will press pump and map. Now the load lock chamber is going to be put under running conditions, and it's going to also scan to see where are the wafers placed. Once the software has mapped the slots in the carousel, we will load the desired one. In our case, we have our wafer in the slot number 1. We just have to press load, and now the machine is proceeding to load the wafer into the chamber. Once the wafer is loaded into the chamber, we have a flashlight here in the machine to check that the wafer has been loaded properly, so we have to turn on the light and check through the window that the wafers is placed properly and the clamps inside the machine are holding it on place. Once the wafer is loaded into the chamber, we have to proceed by selecting the process that we will use. We have 3 standard processes: process B, process A, and auto-clean. In this case, we're going to use the auto-clean. You please press select, don't press process, otherwise you will go straight ahead into processing the wafer. Please press select, and while the machine is selecting the process, you can press the recipe button to modify the values of the recipe. In our case, in that second menu, because it's only an example, we're going to use only like 2 minutes of auto-clean. And also, I'm going to show you how to perform a helium leak-up test. You should do that like probably at the first round of your day to check that there's no major leak of helium coming from the cooling side of the wafer. In order to do that, you press enable, don't touch anything else, and just save the recipe. Once we save the recipe and the recipe has been selected, you only need to press process. As we can see, now the gases are stabilizing. As we can see here, we have the wafer inside the chamber, and also we have like pale blue, that it just changed it to magenta. When we see that change of color, means the process just started. When the process starts, we will have to record the remaining values in the log. They are the 4 gas fluxes, the C4, F8, the SF6, and the oxygen. In our case, the auto-clean only use O2 flux, so only have a flux of oxygen. We also will have to record the cold generator power that it's placed here and the platen edge. We will have to record the cold generation for passivation and etching. In our case, we only have for etching. We also have to record the APC and the process pressure, and if we did a helium leak-up test, the helium leakage. If you have any problem finding any of the parameters, you can only leave the cursor on top of the window, and a yellow window will pop up telling you what is displaying. Once the process has completely finished, you will see that the wafer color will change from brown to green. Once that it's done, the next thing to do is just unload the wafer. It's very easy. You go to the transfer window and press unload, and we'll see how the wafer it's gonna be returned into the load lock chamber. Once the wafer is in the load lock chamber, the next thing to do is to press vent and wait until the chamber is into atmospheric pressure. Now the low load chamber is back into atmospheric pressure, so we open it, we grab the wafer that we just processed, we put it on our box, wafer box, we keep it in a safe place, and the next thing to do is put the carousel chamber into standby pressure. We do that by clicking pump only into the transfer window. Because we won't be processing anything else, and nobody is after us. We will go to the edit menu, go again to operator mode, and press monitor to put it into standby. Once we've done that, the next thing to do is to log off from the laptop. So that's it for like the operation of the STS. If we have any doubts, please contact staff, but you can also check the SOP for the STS and also the complementary videos that explain more in detail each step of the operating procedure.
Now you guys know, right, that how DRI system can be used, but like I said, I will show you an example where you can appreciate the advantage of DRI. So here you can see what we have done. We have used DRI to etch cantilever, to fabricate a micro cantilever, and you can see the smooth wall that is created with the help of DRI. Right. If you take an example of wet etching, you will not be able to release the cantilever in this particular fashion through bulk micromachining. It is very difficult, very difficult. Okay. So, and it is not that wet etching is not good compared to, and dry etching is better. It is, I am not claiming that. What I am claiming is that dry etching plus bulk micromachining in the case of fabricating devices such as micro cantilever is a right approach to fabrication. Right. So, here we have fabricated a piezoresistive micro cantilever, and what it consists of? It consists of a piezoresistor, as you can see here clearly. It has an SU8 tip, it has a cantilever beam, contact pads which we can see here, right. And what is the fabrication process? So, this is a SOI wafer, it is a silicon on oxide, right, silicon on insulator wafer, and we are growing a oxide, then we are creating a window, then we are diffusing piezoresistor, we are opening the contact, we are creating a contact of gold which is contact pads, right. It is all the way from here to here, okay, contact pads, and after the contact pads are created, right, what we are doing, we are creating we are depositing a layer of silicon nitride. The point of depositing silicon nitride is to compensate the stress that is that happens in the wafer because of silicon dioxide. So, there is a compressive stress that is that comes into play because of silicon dioxide, and to compensate that compressive stress we have to use silicon nitride. Okay. So, if you do not use silicon nitride, you can see here that without silicon nitride the cantilever is bent because of the stress induced by silicon dioxide. So, once you have your piezoresistor, you deposit silicon nitride, right, and after that you create your you etch your wafer from the top, you can see here, right, to create this structure, and then from the back side you start etching until you reach this oxide layer. Finally, you have to break this wafer, break this chip from the entire wafer, and you can obtain a single micro cantilever, right. It is very easy now. I hope that you can understand the process flow of how to fabricate a piezoresistive micro cantilever, right. Again, the piezoresistor is formed by diffusing boron into a polysilicon, right, or single crystal silicon. So, you can diffuse boron and that is how you can create a piezoresistor. Okay. So, let us now see wet versus dry etching, right, wet etching versus dry etching. So, and we will compare both wet etching versus dry etching, and see. So, wet etching process can be batch process where multiple wafers are etched at one time, right. You can place in a beaker, right, multiple wafers, and you can etch at one time. If the chemical is there, it will etch all the wafers at one time, right. But in the case of dry etching, most of the time a single wafer or few wafer are processed at one time. So, that is the difference. Second is wet etch process are limited to feature size of 3 micron or larger, limiting their use in nano manufacturing to bulk process, right. So, that is a disadvantage, while in case of dry etching, fine feature size few nanometer can be processed, right. However, wet etching can be used to remove sacrificial layer present in MEMS devices, but dry etching cannot. Dry etching cannot be used to remove sacrificial layer. So, that is the advantage of wet etching, right. Same way, wet etch is also used for resist stripping, right, while dry etching can also be used for resist stripping. Both can be used for stripping out the photoresist. Finally, wet etching is low cost, high throughput, high selectivity, right, while the dry etching is highly anisotropic, but costly and average throughput, right, highly anisotropic, costly, but average throughput. So, that is a comparison between your wet etching and dry etching, right. Now, if we further want to go and understand how the thin film is deposited. So, thin film is deposited using two techniques. One technique is physical vapor deposition that we already discussed, right, and another technique is chemical vapor deposition. So, in the next module of this particular series, we will be looking at chemical vapor deposition techniques. Okay. So, physical vapor deposition we have already seen that physically transfer material from a source to substrate. Example is evaporation, sputtering. In evaporation we have seen thermal evaporation and E-beam evaporation. The other advantage of physical vapor deposition is there is no chemical reaction involved, no byproducts, generally processed after creating very high vacuum about 10 to the -6, but the disadvantage is poor step coverage, right. The step coverage is not so cool in case of PVD. But when you take the case of case of CVD, right, you can see here very clearly poor step coverage when you use PVD, but if you take CVD you have a good step coverage, you have a good film quality, right. It is used to deposit silicon and dielectrics like silicon oxide, silicon dioxide or silicon nitride, right, and CVD is a process used to produce high purity, high performance solid materials, right guys. So, what are the kind of chemical vapor depositions? What are the kind of chemical vapor depositions? We will see in the next module. In this module, what we have seen? We have seen use of a novel technology or a use of a different idea to fabricate a microsensor, right, with a higher mechanical stability while obtaining the temperature at way lower power. Then we have also seen an example, quick example of an actuators which is driving a micromirror, and then we have seen an example of a cantilever where we can fabricate using bulk micromachining, and then we have seen dry etching versus wet etching, its advantages, disadvantages. Finally, what we are looking at is PVD versus CVD, and we have seen its advantage, disadvantage as well. In the next module, what I want to show it to you is a kind of chemical vapor depositions, right. We will talk about few chemical vapor depositions, and that will be the end of this particular lecture, and then we will see some other techniques in the next lecture. So, for this module just go through it whatever I have taught, and I will see you in the next module. Till then you take care, have fun, bye.